It's crazy to think, right? All this buzz about quantum computers, how they could change everything. But making them actually do something, it's almost like you're trying to solve a puzzle, but the pieces are invisible.
Yeah, you hit the nail on the head. I mean, we humans think about these high-level algorithms, big picture stuff.
Yeah.
But the quantum hardware, it needs super specific instructions, low-level detail.
That's like a language barrier.
Exactly. It's like translating, taking our ideas and turning them into something a real quantum computer can run.
Right.
We call it compilation. And it's way tougher in quantum than what we're used to.
Okay, so when you say translation, my brain immediately goes to classical computing. We code in languages like C++A or Go, right? And then there are these tools, LLVM, GCC, they just kind of magically turn that into computer speak.
Right. And those classical compilers have been honed for decades. We figured them out.
So what's the holdup in the quantum world? Why is it so tricky?
It boils down to quantum compilation being a baby, basically, still in its early stages. We don't have that deep well of research and best practices that classical compilation has. And that leads to some big challenges.
Challenges? Like, what are the major roadblocks we're hitting when we try to make these quantum programs run smoothly?
Well, the first one is a bit embarrassing almost.
Yeah.
There's no real agreement on the best way to do quantum compilation in the first place. Like different research groups, different companies, they're all experimenting. But there's no consensus on the most effective techniques or how to combine them.
So it's kind of like a free-for-all out there in quantum software land.
Yeah, you could say that. And then things get even more complicated because of what we call vendor lock-in. The big names like IBM with their Qiskit, Quantinuum with TK-ET, AWS Bracket, Microsoft Azure Quantum, they each have their own software development kits, SDKs.
SDKs, right. So what's the issue with that?
The issue is they don't play nice together. A program written for IBM system using Qiskit might not work on a Quantinuum machine using TK-8 and vice versa. It's very limiting.
Like being stuck with one type of charger for all your devices. Really frustrating.
Exactly. And it's not just about compatibility. Even the latest and greatest research, the cutting-edge stuff in quantum compilation, it takes time to filter down into those mainstream SDKs.
So all the new breakthroughs, they're just stuck in research papers for a while.
Pretty much. And that brings us to the last big challenge. User control. Or rather, the lack of it. Typically, these SDKs offer a few preset optimization levels, right? Like prepackaged bundles of compilation steps.
I see, kind of like choosing between low, medium, and high settings.
Yeah, exactly. But the problem is, you as the user often can't fine-tune what you want the compiler to prioritize. What if you need speed over accuracy? Or vice versa? The current systems don't always give you that granular control.
That makes total sense. Different tasks would need different things from the quantum computer. Now, you mentioned this phase ordering problem before. I have no idea what that is.
Oh, right. That's a good one. It's something that's plagued classical compiler designers forever, too. It boils down to this. The order in which you apply those compilation optimizations, those tweaks, it can drastically change the final code quality.
So like baking a cake. You can't just throw all the ingredients in at once?
Right. Doing one thing before another might open up new possibilities, make things way better, but figuring out that perfect sequence every time, for every program, for every machine, well, it's a nightmare.
It sounds like trying to plan a huge project. The order you do things in totally affects how efficient it is.
Perfect analogy.
Perfect.
And this problem is just as bad, if not worse, in quantum compilation. With all these quantum-specific techniques popping up, figuring out the optimal order to use them, that's a major hurdle.
Okay, so just to recap, we've got no consensus on best practices. We've got this vendor lock-in problem, slow research adoption, limited user control, and this phase ordering headache. So where do we even begin with this deep dive? What are we trying to figure out?
Today's focus is a super exciting new approach to quantum compilation. Researchers are using something called reinforcement learning, or RL for short.
RL, like AI.
Exactly. It's where an AI, an agent, learns to make decisions through trial and error. It gets rewards for doing good stuff, producing better code. And the cool thing is, this isn't totally new. It's been inspired by RL's successes in optimizing classical compilers.
So we're stealing a page from the classical computing playbook and seeing if it works in quantum. I like it. Let's dive a bit deeper into that connection between classical and quantum compilation. You mentioned something called an instruction set architecture, or IS, in classical CPUs. What's the quantum equivalent of that?
Okay, so in a classical CPU, the ISA is like its rule book. It defines the basic operations the CPU can do directly. Any code you write, it has to get translated down into those basic instructions.
Yeah.
That's what the compiler does. Now, in quantum, we have these things called quantum circuits. They're sequences of quantum gates.
Quantum gates, those are like the
Yeah.
individual actions, right?
Exactly. And different quantum hardware platforms, they each have their own set of native gates, the things they can actually physically do. Just like a classical compiler targets the specific ISA, a quantum compiler needs to translate any circuit into the native gates of a particular quantum computer. They're like the computer's most basic building blocks.
So native gates are kind of like the quantum version of those CPU instructions. Makes sense. Now, we talked about the limitations of quantum compilers right now, but could we break down each of those 4 points a bit more? Like, why is each one so problematic?
Sure. Let's start with the lack of agreement on best practices. The impact of that is basically the field is still in this wild exploration phase. Every research team is off doing its own thing, trying different techniques. We haven't yet figured out universal benchmarks or ways to compare them objectively. It's a lot of uncertainty.
And that lack of a standard then feeds into the second problem, that vendor lock-in thing, right? Everyone's making their own potentially incompatible solutions.
Right. Each company has poured tons of resources into their own hardware design and their software. And their compilers are made specifically for that hardware, those native gates. So the compilation process in Qiskit, totally different from TKK or Bracket.
So you're stuck in one EDA system.
Exactly. If you want to try a different quantum computer, you might have to rewrite your whole program, your compilation strategy. It's super inefficient.
Okay, and what about that slow integration of research? Why is there this lag between the new stuff and the actual tools people use?
Well, imagine taking a fresh research breakthrough and putting it into a real-world software package. It's not just a quick copy-paste. You have to test it rigorously, make sure it's stable, doesn't break anything.
Right, it's got to be robust.
Exactly. And the teams behind these SDKs, they have their own plans, their own priorities. They might not be focusing on integrating the very latest academic findings. It takes time.
So the new research is just sitting there on the shelf.
And then the last issue, limited user control over the optimization goals. It's a problem because different quantum tasks need different approaches, right? Imagine you're using a quantum computer for drug discovery, running a complex simulation.
A very important task. You want to get it right.
Right, and you might need the most accurate result possible, even if it takes longer. But then, what if you're doing something else where speed is key, like high-frequency trading?
Yeah.
You want the fastest result, even if it's a bit less precise. The SDKs, as they are now, they don't always give you that fine-grained control.
So you're forced to pick from a few preset options that might not be ideal.
Right, it's like having only a few basic settings on a camera. No fine-tuning.
So all this considered, using reinforcement learning to automate this whole quantum compilation thing, it starts to sound pretty genius. How does it actually work, though? Like, how do you apply RL to this?
The big idea is instead of humans trying to design the perfect compilation pipeline, we let the AI figure it out. We give it an environment to play in, which is basically the process of transforming a quantum circuit.
So the AI is like a student learning on the job.
That's it. It tries different things, different sequences of compilation passes, and when it stumbles upon a good outcome, a circuit with high accuracy or low depth, it gets a reward.
It's learning by doing, by experimenting.
Right. And over time, it builds up this strategy, this policy for picking the best compilation steps. It becomes an expert.
And we mentioned before that using RL for compilation isn't brand new. There's been some success in classical computing, right? What did we learn from that made us think, hey, this might work for quantum too?
The big inspiration was how well RL tackled that phase ordering problem in classical compilers. There was research showing that RL-based optimizers could actually beat the highly tuned systems in things like LLVM, the big players.
Wow, so it's outperforming the best human-made tools.
In some cases, yes. And quantum compilation, it's even more complex. It's changing so rapidly. So researchers were like, hey, this RL thing could be huge here too.
Makes sense. Now, I gotta be honest, when the paper mentions modeling the quantum compilation process as a Markov decision process, my eyes kind of glaze over. Can you break down what that means in a way that normal humans can understand?
Okay, so think of a Markov decision process, or MDP, as a fancy way to describe a chain of decisions. Each decision depends only on where you are right now, not the whole history.
So no baggage, just focus on the present moment.
Exactly. In our case, those situations are the quantum circuit at different points in the compilation process. It starts off in its original form, and as we apply these compilation steps, it changes, it morphs.
It's evolving, like a Pokemon.
I like that. And the decisions are the different compilation passes we can apply at each stage. Like imagine a game, right? The circuit is the board, and those compilation tools are the moves you can make.
Okay, so I'm starting to get it. And we want to make the moves that lead to the best final state, the most optimized circuit.
Exactly. The Markov part just means we don't have to remember every single move we made before. Just focus on the current situation. It makes the learning process way easier for the AI.
So the AI doesn't get bogged down with too much information.
Exactly. Now, the paper talks about walking through the different states and actions in their framework. Want to do that together?
Let's do it. Starting from the very beginning, the initial state.
Okay, so at the start state, we've just got the original quantum circuit, the thing we want to compile. From here, we could do a couple of things. One is apply device-independent optimizations. These are like general cleanup tasks. Simplify the circuit without worrying about any specific hardware yet.
So like tidying up before the real work begins?
Yep. For example, you might cancel out identical gates that are right next to each other, like 2x gates in a row. They undo each other, so get rid of them. Or reorder gates that don't affect each other. Maybe that'll create new simplification opportunities.
It's all about making the circuit cleaner and leaner.
Exactly. Now, the other important action at this stage is quantum platform selection. This is where we decide, okay, what type of quantum hardware are we aiming for?
So are we going with IBM's superconducting qubits or Rigetti's or IonQ's trapped ions? The big decision.
Right, and that choice determines the native gates, the fundamental operations our final circuit needs to use. It's like choosing between Intel and ARM in the classical world.
So huge implications for the rest of the process.
Big time. This selection takes us to the platform chosen state. From there, we move on to quantum device selection. This is where we pick the specific machine.
So if we went with IBM, now we pick, say, IBM Montreal or IBM Washington, getting granular.
Precisely. Each device has a different number of qubits, different connections between them, like picking a specific CPU model. And this takes us to the device chosen state.
Okay, so we know the exact quantum computer we're going to use. Now, how do we make our abstract circuit actually run on this thing?
Here's where the real device-specific work kicks in. Two big things we got to deal with. First, the circuit has to use only those native gates, the ones our chosen hardware understands. Second, it has to respect the physical layout of the qubits on the device, meaning you can't just do operations between any two qubits, only ones that are physically connected.
So physical limitations of the actual hardware.
Right. The first issue, that's handled by synthesis. We basically break down any non-native gates into a sequence of native ones.
Translating into the language the hardware speaks.
Exactly. And sometimes this breaking down process actually reveals more simplification opportunities.
So simplifying by making it more complex first.
Kind of, yeah. It's like taking apart a complex machine to figure out how to make it run smoother. Now, the second issue, the qubit connectivity, that's handled by mapping, which is a two-step process. First, layout. We decide which logical qubit in our program goes to which physical qubit on the device. Then comes routing, where we make sure that the interactions in our circuit can actually happen. We might need to move qubit states around using these things called swap gates.
Swap gates. Sounds like musical chairs for qubits.
Yeah, kind of. If two qubits need to interact but aren't directly connected, we use swaps to bring them together, do the operation, then maybe swap them back. It's like rearranging furniture to make space.
Makes sense. So ideally, after all this synthesis and mapping, we hit the done state and our circuit is ready to go.
Right. It's all native gates, respects the layout, good to go. But there's a twist. We can actually do more optimization steps in the device chosen and only native gate states too. So if there's still room for improvement, we can squeeze in more tweaks before we hit that final done.
So it's not just a linear path, it's more iterative.
Exactly. Like a sculptor refining their work. You go back and forth, making adjustments as you see how things are shaping up.
And the paper really stresses how this framework is modular, and it's got some big advantages. Can you walk us through those?
Of course. So each state in the process, start, platform chosen, device chosen, only native gates, done. Each one has clear rules, constraints that are easy to check. Like in the only native gate state. Well, we can just verify that only native gates are being used.
Makes sense. So you're making sure things are on track at each step.
Yep. And the other cool thing is all the actions, whether it's picking the platform, the device, doing synthesis, optimizing, they all have this consistent interface. They take a circuit as input, spit out a modified circuit.
So it's like a universal language for quantum compilation.
Exactly. And this is huge for overcoming that vendor lock-in problem. Because now you can mix and match tools from different packages, Qiskit, TKET, whatever works best.
It's breaking down those walls between the ecosystems.
Right. You get the best of all worlds. And it also means new research can be integrated more easily. No more waiting for those SDK updates.
So it's more agile, more future-proof.
Exactly. Now, let's talk about how the AI actually learns within this framework. The paper mentions using OpenAI Gym, which is like a gym for AI, I guess.
Yeah, I've heard of it. It's a popular toolkit for reinforcement learning.
Right. It gives you this standardized way to define and interact with RL environments. So the researchers use it to set up their quantum compilation MDP. They define the states, the actions, how the circuit changes.
And how does the AI know if it's doing a good job? That's where the reward function comes in, right?
That's the key. The reward function tells the AI what good looks like. The researchers actually use 3 different ones. First, expected fidelity, which is basically how reliably the circuit will run on the hardware, taking noise into account.
So higher fidelity means a more accurate result.
Right. Then there's critical depth, which is a measure of how long the circuit takes to execute.
Yep.
Lower is better. And their third reward function was just an average of the first 2, so trying to balance accuracy and speed.
So the AI is trying to hit a sweet spot depending on what we prioritize.
Exactly. And it learns through trial and error. It tries stuff, sees what happens, and the reward tells it whether it's on the right track.
It's like a game with a score. The AI wants to get the highest score.
Perfect analogy. And to help it make decisions, the AI also gets these observations, basically features extracted from the circuit.
So it's not just blindly trying stuff. It's getting some information about the current state of the circuit.
Exactly. They use features like the total number of qubits, the circuit depth, and some more complex ones that capture things like entanglement, parallelism.
So it gets a sense of what the circuit is actually doing.
Right. And to actually train the AI, they used an algorithm called proximal policy optimization, or PPO. It's known for being stable and working well across a variety of tasks.
So they had the environment, the rewards, the observations, the algorithm. What about the results? Did it actually work? Was the AI able to improve things?
The results were super promising. They trained their models on a set of 200 circuits from the MQT bench library. This is a standard set of benchmark circuits.
So a good variety of real-world problems.
Exactly. They trained 3 models, one for each reward function. And then they tested them against the built-in optimizers in Qiskit and TKT using the highest settings on an IBM quantum computer called IBM Washington.
So head-to-head against the heavy hitters. What happened?
In the vast majority of cases, the RL-based system produced circuits that were just as good or better than the existing tools.
No way. The AI was beating the best human-made compilers.
Yep. For fidelity, their method was better than Qiskit in 73% of tests and TKT in 80%. For critical depth, even better 84% and 86% improvement over Qiskit and TKT, respectively.
So consistently finding more efficient ways to prepare the circuits.
And the average amount of improvement was significant, too. They saw a 4.9% increase in fidelity and a 22.6% reduction in critical depth compared to Qiskit. Even better compared to TK now.
Wow, that's not just a little tweak, it's a whole new level of performance.
Right. And another interesting finding was the model trained for a specific goal, like maximizing fidelity. It actually did achieve the best results for fidelity. So it was learning what we wanted it to learn.
So this is proof that taking ideas from classical computing and applying them to quantum can really pay off.
Absolutely. This research shows that AI-driven optimization has huge potential for quantum compilation. We can automate this complex process, overcome those vendor lock-in issues, get better performance, and make quantum computing more accessible.
So for our listeners out there, why should they care about this? Why is this AI-powered quantum compilation research important for them?
The big takeaway for you is, this could make running quantum programs way easier in the future. You wouldn't have to be an expert in compilation or be tied to one specific hardware provider. Just write your program and let the AI handle the optimization.
So it's democratizing access to quantum computing, in a way.
Exactly. It's a potential shortcut to getting the most out of these incredible machines.
So as we wrap up, what's one final thought you want to leave our listeners with? Something to ponder on their way home?
Well, think about this. Quantum hardware is evolving rapidly. So are the algorithms we want to run. Given that, how might these AI-driven compilers change the entire landscape of quantum programming in the next few years? Could we see compilers that adapt to the quirks of each individual quantum processor, maybe even in real time?
Wow, that's mind-blowing. A compiler that's not just a translator, but an active partner in the computation.
Right. And the best part, this framework is open source. They've got it on GitHub as part of the Munich Quantum Toolkit, so anyone can explore it, play with it.
So if you're listening, go check it out. And that's a wrap for today's deep dive. Thanks for joining me. It's really an exciting time to be following this fusion of AI and quantum computing. Who knows what incredible breakthroughs are just around the corner?